Welcome to the deep dive. Today, we're getting into something we see all the time, but maybe don't think too much about: thermometers.
Yeah, that little number on the display or that red line going up
hmm
seems simple.
Right, exactly. But there's some really cool physics packed into how they actually work. We've got some great source material to dig into.
You do. It breaks it all down nicely.
Okay, but before we get into the nitty gritty, the mechanics, let's pause on the really big question here. And maybe, slow down just a touch for this one. Is temperature actually the same thing as heat?
Hmm.
Just hold that thought. Because figuring out why they're different, well, that's kind of the whole point of this deep dive, isn't it?
It absolutely is. That difference is super important. So our mission today, we want to help you get a solid handle on this. We'll look at the science definition of what a thermometer measures, explore the different kinds of devices out there that actually measure this energy transfer, and talk about why getting that reading right matters so much. Everywhere from a science lab to just making sure your dinner is cooked properly.
Okay, let's start with the science bit then. That number you see,
Hmm.
or the line in the tube. What is it actually telling us? It's more than just hot or cold.
Right. So scientifically speaking, a thermometer, it's actually measuring the average kinetic energy of the particles in whatever you're measuring, the atoms, the
It's
molecule.
kinetic energy.
Energy of motion, right? Exactly, motion. So the faster those tiny particles are zooming around, vibrating, spinning, the higher their kinetic energy, and boom, the higher the temperature reading you see on the thermometer. There's a direct link.
Okay, hold on. Why average kinetic energy? That word average seems important. If I have, say, a big block of steel and a tiny drop of water, both at 50 degrees Celsius,
Right.
are the particles moving the same?
Ah, great question. That gets right to it. And yes, they are. If they're both at 50 degrees, the average kinetic energy, the average speed, basically, of the particles in the steel is the same as the average in the water.
Huh.
That average is what temperature is. Now, the steel block obviously has way, way more particles total, and that difference relates to the total heat energy, which we'll get to later. But the average motion, identical at the same temperature.
Okay. Simple, but
Yeah.
critical. So particle motion gives us the reading,
Yeah.
and we measure this motion using a few different scales, right? Celsius, Fahrenheit are the common ones.
Yep, degree and
Yeah.
degrees Fahrenheit.
Yeah.
And then you've got Kelvin, K, which scientists use a lot.
Kelvin. That's the one with absolute zero.
That's the one. What's really neat about Kelvin is that 0 Kelvin, absolute zero, that's the theoretical point where all particle motion just stops, completely ceases. So since temperature measures that motion, the Kelvin scale ties directly back to the kinetic energy idea. You can't have less than 0 motion, so you can't have negative Kelvin. It makes perfect sense physically.
That really does connect temperature and motion clearly. Okay, so outside of physics labs, why do we care so much about tracking this average particle speed so carefully?
Well, the sources point to 3 main reasons why it's vital in everyday life. First, think big picture: climate and weather, understanding how energy moves around the planet.
Right, monitoring global temperatures.
Exactly. Second, it's all about control and processes. Think about making steel or complex chemical reactions in industry or science labs. If your temperature's off even a tiny bit,
Disaster, the whole thing could be ruined.
totally, or worse. And the third area is safety, much closer to home. Checking for fevers, making sure medicines are stored correctly.
Or making sure your chicken is cooked all the way through so you don't get sick.
Precisely, which brings up a good point from the material. Think about a science lab, maybe mixing chemicals, or just your kitchen, baking something. Why is controlling the temperature so critical in both those places?
Well, in the kitchen, like we said, food safety. Getting that internal temperature right kills the bad stuff, the bacteria, in a lab.
Yeah.
It could be about making sure the reaction goes the way you want, right?
Yeah.
Too hot, maybe does something else.
Exactly. Or it could even be dangerous, run away, cause pressure buildup. Explosions aren't usually planned.
Yeah, good point. Tiny margin for error sometimes.
For sure. And getting that safety, that precision, you need instruments that reliably turn that particle movement into a number we can read. And all thermometers, no matter how they look, work, because heat moving around energy transfer causes some kind of predictable change in the thermometer itself.
Okay, so that leads us to how they work, the different ways they measure that change. You said 3 main principles.
That's right. 3 fundamental ways. Let's start with the absolute classic, thermal expansion.
Like the old mercury or alcohol thermometers.
Exactly. Liquid and glass. So heat flows into the liquid inside, maybe alcohol, maybe mercury back in the day, though that's toxic.
Right.
And the kinetic energy of those liquid particles goes up. They move faster, bump harder, need more room. So the liquid expands Takes up more volume and gets pushed up that skinny little tube. We just read how far it went.
Simple and visual. Okay, what's next? Moving into the digital age.
Yep. Principle number 2, electrical changes. This is the magic behind most digital thermometers. They use these special little bits of electronics called thermistors or thermocouples.
Okay, how do those work?
Well, a thermistor is basically a resistor, something that resists electrical current. But its resistance changes in a really predictable way with temperature. Hotter it gets, the resistance changes, the circuit measures the change in voltage and translates it into a temperature. Super fast, super accurate usually.
And thermocouples. Similar idea.
A bit different. They generate a tiny voltage themselves when you join two different types of metal wires together and heat the junction. That voltage is directly related to the temperature difference, also very common in science and industry.
So in both cases, heat energy gets turned into an electrical signal you can measure.
Clever. Okay, what's the third principle, the no-touch ones?
Right. Radiation, this is for infrared thermometers. Here's the cool part. Everything that has a temperature above absolute zero, which is like everything gives off thermal energy as invisible light, electromagnetic waves, specifically infrared light.
Heat radiation.
Exactly. So an infrared thermometer, sometimes called a pyrometer, just has a lens to focus that infrared light coming off an object onto a detector. It's essentially seeing the heat being radiated. That's how it can measure your forehead temp or a hot engine instantly without touching it.
So it doesn't matter how it works, liquid expanding, electrical change, sensing radiation if the thermometer says 25 degrees Celsius.
Yep.
The basic truth is the particles in whatever it measured have way more average kinetic energy than if it read, say, 10 degrees Celsius.
That's the core idea. The instrument just needs a reliable physical trick, one of those three principles, to turn that kinetic energy level into a number on a scale we understand. Okay, let's make this concrete. The source material had a little comparison idea. Imagine you've got three things. The cold air outside today, the air inside this reasonably warm room, and maybe a cup of warm water you just made tea with.
Okay.
Which of those three would have particles with the greatest average kinetic energy, and why?
Well, you just have to think about which one is warmest, right?
Yeah.
Assuming the warm water is the hottest. Let's say it's 50 degrees C. Maybe the room is 20 degrees C. Outside is 5 degrees C.
Sounds about right.
Then the water. Definitely the water. Its particles are moving the fastest on average. They're buzzing around, bumping into each other more energetically, trying to spread that energy out.
Makes sense. So speaking of different scenarios, the thermometers themselves are specialized. You wouldn't use a meat thermometer to check the weather. Let's run through the main types the sources mentioned.
Sure, we already touched on the mercury or alcohol thermometers.
Yeah.
Simple, cheap, use thermal expansion, but they could be a bit slow to respond.
And mercury's a safety issue if they break. Then the digital thermometers. You said thermistors or thermocouples. They're super common now, right? Especially for medical use.
Absolutely. Fast, easy to read, portable. Thermistors are usually the key there.
Okay. Then infrared thermometers, the point and shoot kind. Good for speed and when you can't touch something.
Exactly. Measuring moving parts or, forehead temperatures quickly and without contact.
Yeah.
They can often measure a huge range of temperatures too.
And the last one was interesting. The bimetallic strip thermometer. Sounds kind of old school, but still used.
Oh yeah, they're workhorses, often found in oven thermometers or thermostats for your house heating. It's clever physics again.
How does that work?
You take two different strips of metal, like brass and steel, and bond them together like a sandwich. Now, different metals expand and contract by different amounts when you heat or cool them.
Ah,
So when this bonded strip gets hotter, one metal tries to get longer than the other. Since they're stuck together, the only way they can manage that is to bend.
it curls up.
Exactly. It bends or curls. And that physical bending motion is connected to a pointer or a dial. Simple, robust, no batteries needed. Pretty neat.
That is pretty neat. Okay, thinking about all these types, the source material posed a safety question. Which type is generally the safest for everyday use, say in a school or at home?
Well, given what we said about mercury being toxic if the glass breaks,
Right.
it's pretty clear that digital or the alcohol-based liquid ones are much safer choices for general use.
Yes.
Safety first, always.
Definitely. But okay, you pick the right type of thermometer, but if the reading itself isn't accurate, it's kind of useless, isn't it? Whether you're baking bread or doing chemistry.
Absolutely critical. And our research highlighted 3 key things you always need to check to make sure you're getting a good reading.
What's number one?
Number 1, top of the list, calibration. Is the thermometer actually reading correctly? Does it read 0 degrees C in ice water and 100 degrees C in boiling water at standard pressure? If it's off by a degree or two there, it's going to be off everywhere. That's your biggest potential error source.
Right, gonna make sure it's starting from the right place. Okay, what's second?
Second, seems obvious, but check your unit of measurement. Are you reading Celsius or Fahrenheit? Mixing those up. Well, it's caused some pretty famous and expensive mistakes in the real world. Always double check degrees or degrees Fahrenheit.
Good reminder. And third, you mentioned something specific for the liquid ones.
Yeah, for liquid and glass types, you have to read the meniscus level correctly. The liquid surface isn't perfectly flat. It curves down a bit in the middle because of surface tension. That curve is the meniscus.
Ah.
You need to read the temperature right at the bottom, the lowest point of that curve. And crucially, your eye needs to be level with it. If you look down or up at it, you get parallax error, and your reading will be slightly off. Small detail, big impact on accuracy.
Details matter, which probably explains something else from the sources.
Mhm.
Why sometimes you might use two thermometers side by side measuring the same thing but get slightly different numbers.
Yeah, that happens. It could be a few things. Maybe one reacts faster than the other. Maybe, like we just said, one is calibrated slightly better than the other.
Or user error.
Or user error. Like not waiting long enough for the thermometer to actually reach the same temperature as the thing it's measuring.
Yeah.
That's called reaching thermal equilibrium. If you pull it out too soon, the reading's wrong. The more similar the thermometers are and the more careful the user, the closer those readings should be.
Okay, so let's try and wrap this up. Pulling it all together. We know a thermometer is measuring the average kinetic energy, the average motion of particles.
Sure.
We know that in those traditional liquid ones, the liquid goes up because of reliable thermal expansion when it gets hotter.
Check.
And those cool infrared ones work by detecting the invisible heat radiation that objects give off.
Check. Those are the big three takeaways on how they function.
So thinking about the real world now, reflect for a moment, listeners. Can you think of a situation where getting that temperature reading exactly right isn't just convenient, but absolutely essential? Maybe even life or death.
Ooh, good one. There were so many. Maybe storing vaccines. They need very specific, narrow temperature ranges to stay effective. Get it wrong, and they just don't work.
Or think about industrial processes, like making sure the metal in a jet engine turbine was treated at the precise temperature so it doesn't fail mid-flight.
Yeah, the consequences can be huge.
Yeah.
It really drills home the importance of accuracy.
Which brings us back full circle to where we started, that tricky distinction, the one the sources flagged as kind of a bonus challenge, why heat and temperature are not the same.
Right. We've nailed down temperature. Temperature is about the intensity of the particle motion, that average kinetic energy. Hot coffee has a high intensity, high temperature.
Okay, so if that's temperature, what's heat then?
Heat. Heat is about the transfer of energy.
Hmm.
It's the total amount of thermal energy that moves from a hotter thing to a colder thing because there's a temperature difference. Think about that tiny cup of super hot coffee versus a huge swimming pool that's just lukewarm. The coffee has a much higher temperature, right?
Right.
Higher average particle speed. But that massive swimming pool, it contains vastly, vastly more total thermal energy, more total heat content, simply because it has so many more water molecules in it, even though they're moving slower on average.
Ah. So temperature is like the speed limit of the particles, the average intensity,
Yeah, good analogy.
while heat relates more to the total amount of energy involved, which depends on how much stuff there is and its temperature.
Exactly. Temperature measures intensity. Heat is about the total energy transferred or contained. So next time you glance at a thermometer, remember you're seeing the average particle speed, the intensity, not the total energy load. Understanding that difference, that's a huge step into the world of thermodynamics.
A really cool distinction to keep in mind, definitely something to think more about. Thanks for diving depth with us today.